Greetings, thank you for joining us today. Today's webinar is titled IC Quant, What are Factors and How are they used in Quantitative and Discriminate Analysis? I'm Wes Walker and I'll be your presenter today. Today's agenda will include an introduction, then a section on spectral treatments, a section on chemometrics, the journey from K-matrix to PLS, discriminant analysis, and an example setting up a control loop with a React IR and an RC1 reaction calorimeter. The interest of METTLER TOLEDO AutoChem can be divided into four main segments. 1. Using reaction calorimetry and laboratory automation to optimize reaction conditions in thermodynamics. 2. In situ mid-IR analytics to monitor component concentrations during a reaction. 3. Particle characterization tools that enable scientists and engineers to use real-time particle and droplet distribution measurement to make more informed, faster decisions. 4. Software such as ICIR, ICFBRM, ICRaman, and iControl that help the user turn data into information. I want to talk a little bit more about software, as it is one of the key enabling technologies in our workplace today. METTLER TOLEDO's IC software suite was designed from the ground up starting in 2005 to be a complete process development software solution with one common interface that allows not only seamless integration of data, but also full interoperability between instruments. Technologies can now communicate to one another and share information across technology platforms in real time via direct connection or even across a corporate intranet. We have developed modules which we refer to as D2I modules, which stands for data to information. We use chemometrics to simplify data analysis and to make it easy for non-specialists to get the full value out of our technologies. The principal references suggested for a thorough explanation of chemometric concepts are Chemometric Techniques for Quantitative Analysis by Richard Kramer and Chemometrics, a Practical Guide by Beebe, Pell, and C. Schultz. The goal of the webinar is to provide a conceptual framework for those wishing to learn more about chemometrics in order to use the IC Quant quantitative spectroscopy software package. The mathematical concepts as well as terminology are treated with brevity. Detailed click-by-click explanations of IC Quant as well as application examples are planned for future webinars in this series. Let us now go to spectral treatments. I naught is referred to as the background. This is the spectrum of the instrument. In addition to capturing the effects of the instrument's optics on the source's output, it can be used in some cases to capture solvent or other reaction or process components. Next, reaction spectra are collected. The background is used to divide all of the reaction spectra, yielding transmittant spectra. The transmittant spectra are in turn converted to absorbance spectra. Absorbance is proportional to concentration. In many cases, a concentration of interest can be trended directly from a single peak or perhaps a peak reference to a baseline point. On the other hand, there are chemical and biological systems where absorbance information regarding component concentration or even physical properties of interest are overlapped and not accessible via direct absorbance trending. What are some of the concentrations or properties of interest that one might trend using a spectroscopic tool? In small molecule synthesis, we might look at the concentration of the starting material. Polymer synthesis, viscosity. Fermentation, concentration of glucose. Crystallization, supersaturation, degree of supersaturation. Solvent exchange, concentration of solvents. Sparging reaction mass, concentration of hazardous or impurity forming dissolved gases. There are various approaches to obtain a trend of a concentration or property. For instance, trending a peak height or area. It's easy. It can't account for overlap. Good for control. Using a combination of peaks, for instance a ratio, as in user-defined trends. It's easy. Can account for moderate overlap. Good for control. Components and backgrounds, for instance a solvent background as opposed to an air background. Useful for low concentration work. Induces negative peaks. Can be used in combination with IC quant. Components that are auto-subtracted. It's easy. Not usually used for low concentration work. Not used in combination with IC quant. A first or second derivative of the spectrum. This removes baseline effects, helps resolve overlap. Useful in combination with IC quant. Concert or concentration in real time algorithm, live. It's easy, very useful for characterizing unknown or suspected components. Can't be used for control. Concert Pro. Very useful for analyzing sets of reaction data together. Very useful for analyzing data sets taken with multiple spectroscopies. Baseline offset. Useful for removing the effect of temperature or broad peaks on the baseline. IC quant. Requires preparative work. Very good at handling overlap. Produces explicitly quantitative trends. Good for control. Chemometrics, the journey from K-matrix to PLS. How is chemometrics defined? Chemometrics, in the most general sense, is the art of processing data with various numerical techniques in order to extract useful information. It's according to Richard Kramer. Or, chemometrics is the science of relating measurements made on a chemical system or process to the state of the system via application of mathematical or statistical methods, according to the International Chemometrics Society. Or, mathematical, statistical, graphical, or symbolic methods to improve the understanding of chemical information, useful at any point in analysis, from the first conception of an experiment until the data is discarded. This is according to B.A. Rock. Are the mathematical concepts that underpin chemometrics used in other fields? Absolutely. They are used in other fields where large numbers of variables need to be analyzed simultaneously. These publications are examples of the use of partial least squares, or PLS, in various disciplines. Let us begin at K-matrix. We begin by expressing the absorbance as the product of the absorptivity, lowercase a, by the path length, lowercase b, and the concentration, C. We next condense A and B into one variable we'll call K. Now, the absorbance value at any wave number can be expressed as the sum of components that contribute to the overall absorbance. Putting this into matrix notation, we have A equals Kc. Because there will be no exact solution to the equation due to errors, we solve for a value of K calibration, or Kcal, that minimizes these errors. Now kcal has been solved. We can now begin using the model to predict concentrations. We predict concentrations with the equation C unknown equals kcal times A unknown. We think of K matrix as a hard or explicit model. We need to know the concentration of all the components that affect the absorbance values we're using. What if these are not known? We may use P matrix for these cases. In P matrix, a matrix is built using equations that express concentration as a function of absorbances. Beginning with the matrix equation C equals PA, we define the errors to be PA minus C. So when we build a calibration matrix, we will try to minimize this value. To solve for P, we must first multiply both sides of the equation by the transpose of A. And then skipping some steps, we arrive at the equation circled in red. Going directly to the prediction, we will use the equation C unknown equals P times A unknown. We see that in order to calibrate a P matrix model, we need to only know the concentration of the component or components of interest. Other components still affect the spectrum, and we model these without knowing their concentration. Now, the matrix math imposes a requirement on us. In order for the inverse of A times the transpose of A to exist, A must have as many columns as rows. Because A has one column per each sample and one row per each wave number value, this means that we will need at least as many samples as wave number values in order to compute the calibration matrix. What happens if we needed to use, for instance, the spectral region between 1700 and 700 inverse centimeters to solve the problem? This would require 250 wave number values at a resolution of 8 wave numbers. In most cases, we don't want to collect 250 calibration standards. We'll go over the journey from K-matrix to PLS thus far. We learned that we can make a calibration matrix for a chemical system using K-matrix, provided we know the concentrations of the components that influence the spectrum. We then showed how, by using P-matrix, we can make a calibration without knowing these concentrations, as long as we know the concentrations of the components of interest. We found out, however, that due to the requirement of the matrix operations to produce a calibration, we need at least as many calibration standard spectra as wave number values used. For many applications, this requirement is impractical. Let us move forward to a new coordinate system. We begin with a set of 3 spectra collected from a 2-component, noise-free system. The spectra consist of 3 wave number values labeled A, B, and C. In a real system, these would have numerical values with units of inverse centimeters. Next, we replot the spectra as points in a 3-dimensional space defined with axes for each wave number value. We have not changed the data at all. We have simply replotted it to facilitate the steps we are about to take. In a 2-component noise-free system, the spectra will all lie on a plane. We will rotate the plane so that it lies in the plane of the screen. We have changed the orientation so that it is easy for us to see the data transformation we are about to do. The relationship between the spectra and the axes don't change. The axes could have been shown in their new rotated position. Next, we will draw an axis through the data that minimizes the sum of the squares of the distances from the spectra to the axis. We will call this new axis a factor. There, we've said it. A factor is just an axis created to describe a specific data set. As we will see, using factors instead of wave number axes, we will be able to compress the dimensionality of the data, and we will be able to reject noise from the calibration spectrum set. So far, we have not used enough factors to completely describe the data. A second factor is now added. Using the two factors together, the positions of the spectra can be completely described. Whereas we started out with 3 wave number values to describe the data, we can now describe the data with 2 factors. This is an example of data compression. Using the PLS algorithm in IC Quant, we will routinely compress 100 or more wave number values to a range of perhaps 2 to 10 factors. So we have introduced factors, and we find that they are not mysterious. They are very useful for dealing with overlap spectral data to produce a calibration, and in turn, predictions based on that calibration. What happens next is a technique that chemometricians have adopted in order to increase the efficiency of factor-based analyses. The technique is called mean centering. Mean centering implies that we retain the orientation of the second factor, but we move it to the center of the data set. This is possible because the first factor doesn't contain component-specific information. It is the average spectrum of the data set. In a mean-centered model, the second factor now becomes the first, and the first is discarded. Often, reaction data will have more than adequate signal-to-noise, enabling good detection limits. However, there is no such thing as a completely noise-free spectrum. There will always be noise introduced by the optics and electronics of any spectrometer. In addition to moving on the axis that is coincident with the plane of the slide, the data will move on new noise-induced axes as well. The first 2 axes or factors contain the useful chemical component information and to a lesser degree noise. The third axis or factor, we have drawn here in red, contains only noise, no useful chemical information. Recall, the first 2 factors also describe noise, but they predominantly describe useful chemical component information, so we need these 2. However, the third factor described only noise. Therefore, we will discard the factor altogether. It will simply not be utilized during the calibration or prediction steps of our analysis. We now have demonstrated the 2 major advantages of using factors compared to staying in a native data space. First, we're able to reduce the dimensionality of the data. This lets us produce a good calibration with fewer calibration standard spectra. Second, we can isolate and reject noise from the calibration standard spectra set, as well as from an unknown spectrum. Let us now move to the first of 2 examples of a factor-based chemometric algorithm, Principal Components Regression, or PCR. PCR is simply p-matrix performed using a new and improved data space. If we take one step beyond PCR, we can find factors not only for the spectral data block, but also for the concentration data block. Is there noise in our concentration number? Of course, they're based on measurements of a concentration, perhaps from weighing out material or from a chromatographic technique. There is some finite accuracy that we can ideally improve upon through factor analysis. Using PCR, we use factors derived from the absorbance matrix but we use the concentration numbers as is. In partial least squares, or PLS, a set of factors is derived for the concentration numbers as well. This allows noise to be rejected from the concentration data block. Further, it allows an average of sorts between factors from both data blocks, which will give us additional signal to noise. In the next installment of this series, we will look at IC-Quant's features in depth with respect to factor selection. IC-Quant has an auto-select feature that will choose the proper number of factors for the user. However, this result can be checked and modified as necessary by using a variety of tools in the Results and Diagnostics menu. Why are we careful to select the right number of factors? As we've seen, by using too many factors, we model noise. This is often referred to as overfitting. If we choose too few factors, we discard useful component information. This is called underfitting. Discriminate analysis. The Mahalanobis distance. Recall that we can divide the factors into what we call principal components, those factors that are useful for modeling component information, and non-principal components, those factors that contain primarily noise and that are not useful for modeling component information. The Mahalanobis distance is considered useful at finding samples with concentrations or properties having values near or beyond the extremes of a training set. For instance, let us imagine that the concentration of an intermediate is expected to be between 5% and 10%, and the training set contained calibration spectra with concentrations ranging from 2 to 15%. If a spectrum containing a much higher concentration, for instance 20%, was analyzed, we would expect a noticeably high Mahalanobis distance. That sample would therefore be identified as an outlier. The Mahalanobis distance is expressed in the equation where sigma is the variance-covariance matrix, which describes the dispersion of the data, and mu is the data centroid. We show this graphically on the right with an example of a high Mahalanobis distance and a low Mahalanobis distance. Turning from the Mahalanobis distance to the Ftest, we consider that a spectrum's position plotted against principal components was useful for identifying a spectrum with an extreme concentration or property. On the other hand, the Ftest is useful for finding false samples, or samples where there is a component not present in the calibration or training set. The equations needed to express the Ftest for a spectrum and a factor-based calculation are substantial and are given in the IC-Quant help file, as well as the reference cited earlier. While it is arduous to explain the Ftest mathematically, it is very simple graphically. On the left, we show that a high Ftest value corresponds to a large value on a discarded non-principal component, or, put another way, a factor which describes primarily noise. Example, setting up a control loop with a React IR and an RC1 reaction calorimeter. Because we're able to link the React IR to other AutoChem instruments, we can use a single interface with our IC-Quant result to monitor or control a reaction or process. Step A. A calibration is built by collecting spectra of known concentrations at different temperatures. We do this by first dissolving a solute to make a high concentration sample. We collect spectra while cooling to nucleation. We ensure that only the pre-nucleation spectra are used in the calibration because these are the spectra where we know the concentration. we dilute to the next concentration, and we repeat steps 1 through 4, perhaps 2 to 3 times. In step B, we use the expression circled in red with the RC1 to control the degree of supersaturation.